This is Jack Creel, and I'm going to be going over my calculation answers for homework 5. So the first problem is about cooling down steel balls after they come out of a furnace at 900 degrees Celsius. So we are assuming that the properties of the ball are constant and that as well as the convective heat transfer coefficient. We start by finding the characteristic length, which is volume over surface area, and using it to find the BO number for the system. It's very small. It's less than that key value of 0.1, so we know lumped analysis should be accurate. So we can use the corresponding lumped analysis equation. The only parameter we really need is B still. So that depends on these properties. We just plug and chug. Once we have B, we can rearrange this equation for time, and we will find that it should take about 2.72 minutes to cool these balls from 900 to 100 degrees Celsius. The next part asks us to find the total heat transfer if we're cooling 2,500 balls an hour. So we start by finding the total heat transfer for one ball, which is going to be the mass times the heat capacity of the ball times the total temperature change of the ball. And once we have that, we can multiply it by the 2,500 balls an hour to find the total heat transfer to be about 543 watts. The next problem is about the temperature of the Earth's soil at varying depths after a cold front moves in. So the initial temperature of the surface is going to be higher, 15 degrees Celsius, than the surrounding temperature of negative 8 degrees Celsius because that cold front moved in. So we're assuming the soil can be considered semi-infinite medium since we're talking about the mass of Earth, and the soil properties are going to be constant. This is case 3 from our notes where there's convective heat transfer. So we use the corresponding equation, except we will see that this error function is actually going to go to 0. We can see in the table that for an argument over 4, error function goes to 0. And so we can cancel out this whole term, leaving us with a more simplified equation here, and that's what we'll use to plug in different depth values for x and find the different temperatures at the different depths. And we'll see that as you go deeper into the Earth, the temperature is increasing. This is only 50 centimeters in, and it's already a lot warmer because that cold front hasn't affected the Earth deeper down as much. The next problem is about a block of ice. It wants to know when the block of ice will begin to melt, and it wants us to solve the problem using the analytical one-term approximation method. So we set up our coordinate system. We're going to assume we can disregard any heat transfer from the base of the table into the ice, where we know this is two-dimensional. We're assuming the ice properties and the convective heat transfer coefficient are constant. So we need to find the BO number for both of these planes, and once we have that, we use it with table 4-2 to find these corresponding parameters for the equation we know we're going to use. Once we have both those parameters for both these planes, we're then going to move on. I did this up here, but we know that the first liquid drops, the melting is going to begin at the top corners because that's where there's the most exposed area. So we use that fact with table 4-5 to get this equation here. And then I just combine these two terms because they are going to be the same, so we have them squared here. And then we already know all of these values, so we can set that equal to our equation here. And we already have the parameters as well. I didn't write out all the values here, plug everything in, because that would take a lot of space. But after we plug everything in Excel, we find that this should take about 19.5 hours for the ice to begin to melt. And we also found in there that the tau is going to be equal to 0.241, which is greater than 0.2, so we know our method we're using is applicable. The last problem is for mass diffusion. It's about mass diffusion of carbon from steel beam. And so we use the transient mass diffusion equation here, which would normally just be this equal to this over here. But I am subbing in some of the things from the problem statement because it wants us to find the depth below the surface of the steel at which the concentration of carbon is going to be reduced to 40% from its initial value. So that's where this 0.4 initial concentration comes from. And we also know from the problem statement that the concentration of carbon at the surface is 0 throughout the process. So we put that in there. And then we set the error function equal to 0.6. And once we have that, we can use table 4-4 with that to find the depth where that 40% initial concentration will occur at these different times. It's an hour for part A and 10 hours for part B. And so we will find, using that equation, that after an hour, 40% of the initial concentration will occur about 0.0141 centimeters in, and 10 hours in, it'll be about 0.0445 centimeters in.